A neutron star is a very dense type of star that rotates extremely quickly. If a neutron star has a radius of 15 kilometers, which is the same thing as 1.5 times 10 to the fourth meters, because we got to have things in standard units, and it spins at a rate of 1 revolution per second, we can figure out what its minimum mass must be based on the fact that it doesn't fling itself apart. What is that minimum mass? So we've got this thing spinning around very, very quickly. Say we consider some chunk of its surface, right? There's not really things on top of a neutron star. The force of gravity is so strong that it's kind of just a pulp. But there's some chunk of it on the surface. Let's say that chunk has mass 1. For it to continue to spin in a circle, because we're saying that the neutron star is circular, for it to be able to spin in a circle, it's got to have a centripetal force on it, right? Force centripetal, what's that got to equal? It's got to always be pointing into the center, and it has to equal the mass of the chunk times v squared over r, right? So v squared being actually the speed squared. I'm being a little bit lazy, sorry. Now, what forces is keeping it down? There's nothing holding it down. It's not tension to the surface. The only thing that's holding down is raw gravity. So we know that the force of gravity has to be at least equal to the force centripetal. We could have more than that, right? Because there's pressure inside, so it could be larger gravity than that, because just like you could have more gravity and still be attached to the Earth, you know that the force of gravity has to be at least enough to hold up to the centripetal force. Then there could be a normal force to cancel out that extra gravity, but we know that the force of gravity has to be at least greater than or equal to the necessary centripetal force for that object to stay on the surface. Otherwise, if the force of gravity is less than the centripetal force, the entire neutron star will just explode out every which way, and we won't have a neutron star anymore. So what will that minimum mass be? So let's look at the minimum case is going to be when force of gravity is equal to the centripetal force. So if the force of gravity is equal to the centripetal force, we're going to get that G m1 m2 over r squared equals that mass, the chunk on the surface, times v squared over r. So in this case, let's make that chunk on the surface m1 v squared over r. So m1's cancel out, and we get G m2 over r squared equals v squared over r. So what are we looking for? We're looking to know what the mass of the neutron star is, what the minimum mass is. Remember, we know force of gravity must be greater than or equal to, so the minimum mass is going to be when force of gravity is equal to the centripetal force. So we want to solve for m2. m2 is going to be equal to v squared. We multiply both sides by r squared. That'll leave us with an r up top. We divide both sides by g, so we'll have g on the bottom. So what's v? Well, how fast is it moving around? If it makes 1 revolution per second, then that means how much distance did it cover in that second? So v is going to be equal to distance over time, which is going to be equal to the circumference of the object divided by that 1 second, because it manages to make 1 revolution in a second, right? So the circumference of the object is 2 pi r divided by 1 second, so we're left with just 2 pi r meters per second, right? So that's what the velocity is. We sub that in, and we get 2 pi r squared times r over g, or 4 pi squared distance to the surface cubed divided by g. We plug in a bunch of numbers, all those numbers that we have. So 4 pi squared, what's r? The radius is 15 kilometers, so 1.5 times 10 to the fourth. Now, it's not just squared now, it's not to the 1, it's cubed. We divide this whole thing by g, or 6.67 times 10 to the 11th. Sorry, not 10 to the 11th, 10 to the negative 11th. So what do we get when we punch this all through our calculator? We're going to have to get some pretty large number, right? We've got 10 to the 4th cubed up here, times these other numbers, and then divided by 10 to the negative 11th. So since it's a negative exponent on the bottom, it's going to wind up adding 10 to the 11th to the top. So we punch that all through, and the number that we wind up getting is 1.998 times 10 to the 24th kilograms. So it has to be at least more than a third the mass of Earth. Otherwise, it'll explode out in all directions. And in reality, neutron stars turn out to be way more than that. But we figured out what the minimum is based on this simple thing that we've got right here. The fact that if it was the fact that it's rotating very quickly and it doesn't want to fling itself apart, it's got to have something holding itself in. And we're assuming that it's going to have to be holding itself in through gravity because it's not a solid object. It's under that kind of gravity. It's kind of a soupy mass of things. So to be able to keep itself from flinging itself apart, it's got to have enough gravity to hold itself together. So any object, any piece of itself, any mass of itself must have enough force of gravity to overcome the necessary centrifugal